This film deals with two important ways in which we find out about the world around us. By looking and by listening. Let's start with looking, seeing. In another of these films, we saw that there's electrical activity in the brain which is affected by whether we're looking at something or have our eyes shut. We watched this on an electroencephalograph, and we learned that the information we get through our eyes is received as electrical signals in part of the cerebrum at the back of the brain. How do our eyes work? Here's a model of the human eyeball. We can look inside. There's the outside of the eyeball with parts of the muscles which enable us to move our eyes. This bulge is the cornea, and the lens, which is held in place by ligaments attached to what are called the ciliary muscles. It's possible to take photographs of the lens inside the eye. The lens is that nearly circular object on the right. Now, the lens in the eye is there to focus images, just like, say, a camera lens. But a camera lens is a solid object which focuses by moving in and out in front of the camera. In the eye, the cornea, the bulge on the left, does part of the focusing together with the lens. The lens is flexible and focuses by changing its thickness as the muscles attached to it by these ligaments contract or relax. This alters its focal length so that objects at different distances are brought to focus at the same point on the retina at the back of the eyeball. Now, most camera lenses have what's called an iris diaphragm to regulate the amount of light they let through so that the film gets the right exposure. The eye has an iris too. Watch how it contracts to reduce the amount of light it lets through when a bright light shone directly on the eye. Then it dilates again. Watch again. This makes sure that the right amount of light falls on the retina so that it's not damaged. The iris is just in front of the lens. Here's an interesting point about the iris. In poor light, the iris diaphragm on the camera lens has to be wide open to let through enough light to produce an image on the film. If we now focus it on the distant pencil, the one in front's quite out of focus. But if we let in more light and have to close the diaphragm like this, what's called the depth of field is increased. The pencils are the same distance apart, but when we now focus on the far one, the front one's sharp too. This is why people who can't focus down onto, say, small print held near to them can read it properly in very bright light when their irises contract. In a camera, light passes through the lens and is focused on the film at the back. In the human eye, the light's brought to focus on a sensitive lining to the inside of the eye, the retina, yellow in this diagram, and connected to the brain by the optic nerve on the right. Here's the retina on the model. It contains an enormous number of special nerve cells and needs a good blood supply, which you can see it has. Here's a photograph of the retina in a living human eye. This is where the optic nerve emerges, carrying signals to the brain. It's possible, using computerized X-ray equipment, to get pictures of the eyes, the optic nerves and brain. There's one eyeball and the other. And the optic nerves here and here. Here's the nasal cavity and the brain. You can see the eyes and optic nerves even more clearly on this next slice. How does the retina work? How does it send messages to the brain? Let's look at it more closely. It contains millions of these tiny rods, yellow in the picture. These send electrical impulses to the brain when light falls on them, so that the brain can form pictures of what we're seeing. The rods around the edge of the retina, by the way, are especially sensitive to the movement of light. That's why we so easily notice movement out of the corner of our eye. But we don't just see movement and shape. We also recognize colour.
Lights, hold.
How does the retina detect different colours? Well, particularly here in the central part of the retina, there are cells of a different shape from the rods. They're called cones. Here are 3 of them. There are 7 million in the retina as a whole. Cones detect certain colours. Some of them react to magenta, a sort of red, like the middle one. It sends signals to the brain when this colour falls on it. Others react to greeny-blue light, like the cone at the bottom. Yet others send a signal to the brain when yellow light falls on them. But suppose we're looking at something which isn't red, green or yellow. Well, any colour can be made up from 2 or 3 of these colours. Brown, for example, can be made by mixing red and green. So, when we see something brown, this colour triggers off the cones sensitive to red and those sensitive to green light. The brain receives nerve impulses from these cones and says, "Ah, red and green, must be brown," and so with any other colour.
Now, head whip.
The ways in which our eyes work are very complicated. Those were just simple explanations of some of the things we know about the process of seeing. What about that other very important sense, hearing? Sound waves are pressure waves in the air. They pass down this part of our hearing system called the outer ear. When they reach this, the eardrum, they cause it to vibrate. We can take the eardrum out of this model. It's a slightly transparent disc in a frame of bone. It's this which vibrates when sound waves reach it. At the back of it, there's a train of little bones called ossicles. Here are 2 of them. One's attached to the eardrum. When the eardrum vibrates, this first ossicle vibrates too and passes the vibrations to the second little bone, this one. Here's an actual eardrum with the first 2 ossicles, smaller than the model, of course. Now let's look at the third ossicle, the third of those little bones. Like the others, it's in the middle ear. This is it here. It's called the stirrup. And here are the real ossicles. See how very tiny they are. When the eardrum vibrates, the vibrations are passed on from one bone to another. The stirrup's on the left. It passes those vibrations on to the inner ear. This scientist is working on the ears of mammals, which include us. Here are the ossicles and the middle ear. The eardrum's been removed. These first 2 ossicles transfer the vibrations from the eardrum to what's called the window at the bottom of the cochlea, which is on the right. The stirrup's down here, almost out of sight, and when the first 2 ossicles make it vibrate, it causes the window to vibrate as well. The vibrations of the window send sympathetic vibrations spiralling up through a liquid here inside the cochlea. The vibrations in the liquid make tiny hairs vibrate on these ridges, which causes electrical nerve impulses to travel to the hearing centre of the brain. Here are some of the tiny fringes of hair seen by an electron microscope. Hairs in different parts of the cochlea respond to different sound frequencies. The inner ear, especially the cochlea, is a very sensitive apparatus. If we're exposed to very loud noises without some kind of ear protection, those sensitive hairs can be damaged and we may suffer permanent hearing loss. You can see where some of the fringes of hairs here have been damaged or even completely destroyed by loud noise. Incidentally, over-amplified pop music can cause this sort of damage. The model of the inner ear. The cochlea on the left, and these are the semicircular canals. They also contain fluid, the movement of which, when we move our heads about, causes messages to go to the brain to do with balance. But our eyes also have a lot to do with balance. This girl's blindfolded. Electrodes on her head record the movements of her eyeballs as she spins around. Her brain's receiving no signals from her eyes telling her where she is, and her eyes are moving about, trying to fix on a sight of something. The eye movements are recorded on this paper trace. When she finally stops turning and the blindfold's removed, she's very dizzy.
Did you feel dizzy this time?
Yes.
But if she's able to keep her eyes fixed on something as she rotates, it's a different story. She's looking straight at her fingertip. No movement of her eyes as the trace shows. And when she stops,
Do you feel dizzy this time, June?
no. Ballet dancers make use of that technique.
Now
When they
don't
pirouette,
bend
twisting
your
round
head.
rapidly, they fix their eyes on some definite object, part of the theatre or studio, each time they turn round.
That's better.
It's called spotting, and this prevents them getting dizzy.
Spot with your eyes. Look. That's it. Now see the same spot each time. Whip. Whip, whip.